Hello, hello. Hope you're all doing great. Thanks for accommodating a slightly later start today. We'll still get done the things I want to get done, at least the basics of it. I hope you all are doing well. So, in the last classes, we've been covering Lagrangian mechanics and the implications of using Lagrangian mechanics for control. Okay, and that's really and this is really empowering because like at least for me, like when I was a wee baby uh, PhD student or undergraduate student, you'd have I look at all these like these complicated mechanical systems, and I'd be like, how do I come up with the equations? How do I simulate that? Is a better way. Like, how do you come up with a computer simulation of that? And especially when you have lots of interconnected bodies. I remember one of the projects we had when I was in an undergrad was a trebuchet. We had to analyze how a trebuchet would launch, and we had these very rudimentary analyses, which were basically just projectile motion problems. They weren't really taking advantage of all the really cool multi-body dynamics of like a swinging pendulum, like with a counterweight that swings, and Lagrangian mechanics lends you with such a simple way to model these systems. And the only downside is that kind of cranking through the math can be a little annoying, right? It's a lot of math to crank through. Well, fortunately, we have the MATLAB symbolic toolbox to help us out. Let me pull up. So what we're going to do today is we're going to code up some simple examples using Lagrangian mechanics. Okay, and we will second here. See how far we get today. And we're going to continue with this at the next lecture. We're going to try to do operational space control because you'll recall that there are ways that we can use these dynamical equations to do things like inverse dynamics control. Okay, where we can say, hey, this is the acceleration we want of my system. Okay, well, here we go. Here you got my pen. Got my pen. All right. I want to command its acceleration in this direction. Well, and at this rate, maybe 1 meter per second squared. Okay. Well, if I know my mass and I say I want to go 1 meter per second squared, then I can figure out the force I want to put on it, right? And inverse dynamics that's what inverse dynamics is, and it's an extension of that for all kinds of accelerations on a multi-body system. That's what we're doing. Okay, so let's go over to the board. So today, April 2nd, so we're going to be coding Lagrangian mechanics. Now, we're going to be making good use of the MATLAB symbolic toolbox. So, of course, have your MATLAB open and ready to go. And and specifically, we're going to use the fact that we can take all of these derivatives associated with the Euler-Lagrange equations inside of the MATLAB symbolic toolbox using those tools. And I'll show you how it's going to work here. Okay. So let's try to motivate by doing an example. We've done this example before. We're going to start with the pendulum. We're going to try to move to the double pendulum with the goal of so this is the pendulum. This for my elbow's sake. All right, here we go. Thank you. Thank you for your patience. All right. So we're gonna try to do a single pendulum. We're gonna do a double pendulum. Okay. Single pendulum. We're gonna have just a trying to let's keep it with a. I'm thinking out loud here. Should we do an example that has rotational inertia here? That might be fun. That might be fun. But for now, let's just do a single pendulum. We'll add the rotational inertia to the double pendulum. So we'll just do a single pendulum at the end. There's a bob under gravity with their angle theta from the vertical theta of t. Right? Excuse me. Let's sneeze. Excuse me. All right. So we got that. So now we can just say, hey, minus g over L sine theta. We know that's the right answer, but we're going to derive using Lagrangian mechanics these equations of motion. And here's your double pendulum. Okay. All right. We're going to have one bob and then another bob See, one of which is you have some theta 1, and you have some theta 2. Both are time varying. Say this has a mass 1, this has mass 2. Or let's say they all have, I don't know. That's it, length 1, length 2. This has just some length, right? So we want to get from the single pendulum to the double pendulum. All right, that's where we want to get to today. So we'll definitely get single pendulum done, hopefully, if I am in any ways fast about this. So we want to use Lagrangian mechanics, and we have all the different steps. So let's do it for the single pendulum. First thing we're going to define are our generalized coordinates. Those are the degrees of freedom of our mechanism, okay? Our generalized coordinates. Q of t. Now for the pendulum, it's only one of them. It is theta of t. All right, for the single pendulum, right? Okay, so let's jump into the symbolic toolbox right now. I'm actually have pulled up MATLAB. Pull up MATLAB if you can. All right, so I have MATLAB right here. I'm going to create a new script. I'm going to call it, I'm going to save it. I'm going to call it single pend Lagrange. Okay. All right, single pend Lagrange. I hate that name. No underscores. No underscores. Single pend Lagrange. No underscores. Okay. Single pend Lagrange. .m. All right. Written by me and all of my friends here today. Okay. On this, the 2020 year 2026, 0402 of the common era. Okay. First, we're going to clear everything. CLC, clear the screen. Clear all the variables. Close all the plots. Okay. All right. Now, we are going to start defining things like Q terms of symbolic variables. And this is really interesting. We can start to see the symbolic variables. You'll see they are functions of time, right? Well, we can actually define symbolic variables that are functions of time. And this will be important when we are taking our ordinary time derivatives as part of the Euler-Lagrange equations, okay? So let's do this. Let's say here let's create some symbols. Okay, first symbol, let's make time. Okay. All right, and then we're going to say, hey, let's make some new symbols. You put it in the same line if you want, but I'm going to say theta of t. I'll call theta as th. That's theta, okay? And I can make it a function of time. I'll show you what I mean. Let's run that. Okay, it's running. And if I say, hey, what's theta? It says theta is a function of time. Okay? Nifty, right? And that means I could do things. I could take the derivative of theta with respect to time. I could say the derivative of theta with respect to time is the derivative of theta with respect to time. Oh my goodness. How clever. Who would have guessed? The derivative of theta with respect to time is the derivative of theta with respect to time. But this is going to be important because watch what I can do. So because what's going to happen, so let's say if I want to take the derivative of theta squared. Theta squared with respect to time. It's going to do the chain rule. 2 times theta times the time derivative of theta with respect to time. It does the whole chain rule for you. And that's really important, as we saw when we were doing our Lagrangian mechanics derivations, when we start taking our derivatives as part of the Euler-Lagrange equation. Okay? So we are here defining our angles all of our generalized coordinates as being functions of time. And that'll be useful when we get to the actual Lagrangian. Okay. And furthermore, I can say that Q is a vector containing theta. And I run it. It says, okay, Q is just a vector containing theta. And if I had multiple generalized coordinates, let's say here's our generalized coordinates. Those are our generalized coordinates Q. That's our first step. We've done our first step well. Okay? Now we have to account for all the energies of the system. Okay? And that's going to be all of our potential energies and all of our kinetic energies for this system. So that goes in our Lagrangian. Okay? Account for all of our energies. So that's going to be T, that's kinetic. Okay. And V, that's potential. Our kinetic is going to be 1/2 mv squared. So it's, 1/2, mv dot v, v, velocity vector of your mass, dot the velocity vector of your vector mass. That is the more correct way to say 1/2 mv squared for multidimensional vectors. Okay. And v is going to be mgh, right? Okay. That's the height. And to get these values, you get your height and get your velocity. What I find is useful is to draw a vector from the origin to your masses. That's really helpful. It's a great way to organize your thoughts. So you have this pendulum. Let's say that that's the origin right there. Right? And then this is your mass. Let's draw a vector. We'll call it R. Okay? Now that vector R, assuming that this is like X and Y for the X and Y direction. Okay? If this is length L, then the vector R is going to be L sine theta of T in the horizontal direction for the, opposite over the hypotenuse, and minus L cosine theta of T for the vertical. Okay. Right. So we can write this vector R, and this is helpful because 1, that's your height for MGH. But 2, if we want to get our velocity of that mass, that's R dot. The ordinary derivative R dot. That's your velocity vector. Okay. So we're going to start getting into a little bit of trickiness for how we're going to formulate this in the symbolic toolbox. There are lots of ways to do it, but these are cool tricks that I found. Okay. So I'm going to define a vector pointing to the masses. And this is all, so that's what I'll do that. Okay. So pointing to the masses. So we'll call it R, and it's a vector. The first element is L. I haven't defined L yet. Times sine of theta. Semicolon, because the vector, I'm going to get a column vector. Then minus L times cosine of theta. All right. And notice that I'm leaving no semicolons here, and I just keep hitting and just keep running the script just to make sure everything's working. You can see I didn't define L. So let's define L. Let's define our parameters real quick. Define our parameters. Get up here. Define parameters. Okay, L is equal to 1. M is equal to 1. G is equal to 9.8. Okay? Right? Then these are going to define our symbolic quantities. Okay. Generalized coordinates. All right. And then we have the vector pointing to the masses. All right. So we had, now this should work, right? Run it, should work. Hey, look, R of T. Notice it knows it's a function of time. Okay? By the fact that r was set to be like some sine of theta, and it knows that theta is a function of time, it also knows that r is a function of time. See that? See that? Good. Okay. Powered by this coffee. All right. And so that's our position, right? Now let's get the velocity. We'll call it the derivative of the derivative of the position r with respect to time. We'll call it dr. Okay, dr. Well, that's just the derivative. Diff is the derivative command in the context of the symbolic toolbox. Okay, diff of r with respect to what? With respect to time, right? Okay, and let's run it. And sure enough, look, the derivative of sine is cosine, and here's the chain rule. The chain rule is all figured out right there. See that? Isn't that neat? So that's pretty cool, right? And this is going to be really helpful for defining our energies. Okay? So for our T, it's going to be equal to 1/2 m times v dot v. Okay? Another way to write v dot v, so v dot v, you can write v transposed times v, right? Why is that? I'm glad you asked. Well, it's because if v is a column vector, here's like vx and vy, right? Then v dot v is then going to be, let's say is going to be v transpose times v. It's going to be vx vy. Yeah, this is good. We're going to set up the infrastructure with a single pendulum and then move on to double pendulum next time and do some operational space control. All right, vx vy times vx vy. And if you do this matrix multiplication, this is a 1/2 and a 2/1. Can you make this multiplication? Yes, you can. What's the result? A 1/1. That's a scalar. That's what should come out of a dot product, always a scalar. And it's just vx squared plus vy squared, right? That's the same as the dotting with itself, right? So we can write back in the code, we could say v transpose, and what's transpose in the context of MATLAB? It's the apostrophe times v. So let's look at that t. Let's look at that thing, right? Oh, it's not v. It's a dr. We call it a dr. I'm sorry. Our velocity is now called dr right there, right? This is velocity. Notice how I'm keeping the semicolons off of the script because we kind of want to see what the math looks like. Okay. All right. I ran it. Oh, okay. Here we got this thing, and it looks a little messy. But honestly, the thing that kind of stands out, this is a little trick. You're gonna learn some tricks in MATLAB here and how you're handling the symbolic toolbox. Anyone see that conj right there? What the heck is that? Do you know what that is? Does anyone know who took linear algebra and knows what the conj is? It's the conjugate, the complex conjugate. This is a little MATLAB trick. So, my friends, it has to do with imaginary numbers. I'll show you what I mean. Let's say you have a vector, we'll call it x. Let's say it has 1 plus I. So it's a complex number. 2 plus 2 times I. Here's a vector, right? That's a vector, but it has complex numbers in it. Okay. Now I'm going to take the transpose of x. What's it going to do? It's going to take that row vector and turn it into a column vector, right? That's correct. But notice, these are now negative as opposed to positive. If you've ever done a transpose in MATLAB, that's what it's doing behind the scenes. If there's a complex number, if you have it in there, it will do the complex conjugate. This is called the complex conjugate when it flips the sign of the imaginary component. So in order to be mathematically correct, it said, hey, you're doing, and this is what technically a full transpose does for strange, not linear algebra reasons that we don't need to cover. okay? But you'll notice that that MATLAB's like, what the heck? Okay, I'm going. In order to be mathematically correct, technically, I'm taking the conjugate of all these things. Okay, we don't want that. There's a way to say, hey, I just want the transpose. I don't care about any conjugates of the imaginary numbers. Really simple trick. Instead of saying dr apostrophe, you say dr dot apostrophe. Right there, dr dot apostrophe. Okay, so if I said x dot apostrophe, this is now a column vector with pluses instead of minuses. So it did not flip the sign of the imaginary numbers. Okay, little trick. And as a result, if I run this now, look at my kinetic energy. Much simpler, right? There's no conjugates involved, but there it is. There it is, 1/2 mv squared. Okay. Now for our potential, this is our kinetic energy. And then V is our potential energy. It's mgh. M times G times H. Now we don't know what H is, right? But we don't have an H variable. What we do have is R. And the height is going to be this vertical position here, right? So I'm giving you all the fancy tricks today. All right. So you might say, oh, perfect. If I want to get the height of R, I just grab the second element of R. So my friends, what would you do to get that second element of R? And you're probably like, well, that's easy. I'll just say R. It's a vector, so I'll get the second element, R, open parentheses, 2. What? It gave me both elements. And there's a 2 in there. What? Well, my friends, what is R? It's a function of time. So when you say R, open parentheses, 2, the symbolic toolbox thinks you want to know what R is at time equals 2. And it gives you that. Interesting? You don't want that. We just want that second element. How do we get that second element? I'll show you another trick. Another linear algebra trick. Anyone fascinated by these tricks yet? So our height, if we want to just pull out of, you know, R1 and R2, where R2 is our height, okay, what we can do is we can multiply it by a row vector 0, 1. What will this turn into? This will turn into 0 times R1. That's good because we don't care about R1. Plus 1 times R2. Perfect. So our height will then equal to R2. That's to be our Y position, right? Okay. So let's do that. So we can say our height is going to be just 0. What? 0, 1. It's a row vector 0, 1 times our R vector. And indeed, there we go. There's our T, our kinetic energy, and there's our V. And if we had multiple kinetic and potential energy terms, we would add them all together to get all the energies together. Make sense? Now, we need to do the next step, which is the Lagrangian. Okay? Lagrangian is equal to T minus V. Okay? So we compute the Lagrangian. Perfect. Let's do it. Go back to our code. Okay. Now, keep in mind, we might call it L, but the problem is we've already defined L as length, so let's just call it Lagrangian, or like Lagr is equal to T minus V. Run that. There you go. There's a Lagrangian. Right there. Nifty. So, perfect. What's next step? We're going to use the Euler-Lagrange equations. Now, this is a conservative system. We don't have any non-conservative forces. This is just a pendulum acting under gravity without any friction. There's no external torques, right? Right at the moment, use the Euler-Lagrange equation. It's going to be d dt, that's ordinary derivative, partial L, partial q dot, okay, minus partial L, partial q is equal to 0, okay? So, there are a couple components here. You'll notice that there is this partial L, partial q. Let's compute these in different lines of the code so we can check out each of them and see if we're doing them correctly, okay? This is the simplest one, this partial derivative, okay, partial L, partial q. Let's see what happens, all right? So it's the Euler-Lagrange equation. Let's see what happens when we just try to take the derivative. Sorry, or the EL equations. All right, so we're going to call this term here partial L, partial q. It's going to be, we'll call it dl underscore dq. Okay, we're going to call it that. And that's going to be the derivative, diff, of the Lagrangian with respect to q. Run it. Okay. Turns out fine. Here, this is like the 1/2 mv squared. This is the MGH term, which is correct. Look at that. The thing's right there. All right. Now, I'm going to save you some trouble. Right now, Q, we have how many generalized coordinates in Q right now? How many generalized coordinates? We have 1. 1. But we could have several in future problems. So just to future-proof this code from having multiple of these Q's, we won't just take the derivative here. We're going to take the gradient. So in case Q is a vector. Still works for a 1-by-1. Still works for a scalar Q. But this will work for a vector now as well. Okay? Partial L, partial Q. All right? So now, that's great. Now let's compute this term right here, dl dq dot. And then we'll take the derivative of the respective time. Okay? So how are we going to do that? Well, it would be nice. So let's take the derivative of L with respect to q dot. That term, we'll call that dl underscore d dq, because dq is q dot, right? We'll call that. All right. So let's take the derivative of the gradient. So you take the gradient of the Lagrangian with respect to q dot. Now let's make this a little cleaner. Instead of writing the diff q and t, which I believe will work. Indeed, it does. Beautiful, gorgeous. Oh, I love it so much. I love it so much. Let's do this step up above. It would be nice if we could say Lagrangian with respect to dq. And we'll just define dq up above. Let's go up above. So I can say dq is equal to the derivative of q with respect to time. Generalized velocities. Sorry. Generalized velocities right there. And then I can, down below, say that this term is equal to question. Sorry, which line are you talking about? Line 17. So your question is, do I want to take the derivative here? No. Do I want to take the gradient here? No, I do not. Because this is just the ordinary derivative with respect to what? Time. Time. And time is never going to be a vector. So therefore, you want to take the derivative here. Okay. So, all right. So this should all work. Great. It does. Awesome, cool, neat. All right. Let's move on. So we have this term, but we need to take the time derivative of it. Okay? So let's do that. Let's say we'll call it d. Oh, what do we call this? ddl ddq underscore ddq dt. That's annoying, but it's there. It's the derivative of dl ddq with respect to t. Of course, obviously. So, but all it is just the derivative of this, i.e. that, with respect to time. So let's just grab this, copying, putting it in here with respect to time. Okay? I'll run it to make sure it doesn't cause any errors. Looks like we're doing okay. By the way, you'll notice, my friends, I see a cosine squared times a thing plus a sine squared times the same thing. Anyone remember your trig identities? What does cosine squared plus sine squared equal? It equals 1. So sometimes it's helpful when you're done is you just do a simplify. Okay, but we'll get to that. So if we hypothetically were to simplify this answer, watch this. Simplify this answer. Oh, it doesn't have the answer. Okay, sorry. DL, DDQ, blah, 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 blah. If I were to simplify that hypothetically, theta double dot. So you can simplify it later if you need to, using the simplify command. But anyway, so we have DL, DDQ, DLQ, right? So now the EL equations, what we're going to call this here, this whole thing on the left side, on the left-hand side, we're going to call this the EL-LHS for the left-hand side of the equation. Okay, EL-LHS. So the EL, the Euler-Lagrange left-hand side, EL-LHS, is going to be equal to this term, which is this, copy, minus this term, which is this, copy. There we go. EL-LHS with respect to time. Look at that. Okay. Now we can simplify it because we know that there's that some of the math is it's more complicated than it needs to. We can say EL-LHS. We want it to be a simplified version of itself. Please simplify it. EL-LHS. Simplify the terms if possible. Okay. So Euler-Lagrange. Left hand side. Okay, the right hand side is going to be 0. Here we go. Euler-Lagrange left hand side. Look at that. Okay? Question. So the question I'm getting is that what is this term? What's this comma t comma t? This is just the syntax of taking a second derivative using the MATLAB symbolic toolbox. This is, you want to take the derivative of theta first with respect to t, and then again with respect to t. So what is that? Theta double dot, right? In fact, if you wanted to right now, we could solve this. Hey, this is theta double dot. That's 49 over 5. That's G. That's 9.8. So it's saying theta double dot plus 9.8 sine of theta equals 0. Put that on the other side. Theta double dot is equal to minus G over L sine theta. Minus G over L sine theta. We've seen that many times in this class, right? Boom. Okay? But I am generalizing how to, how to set up the Lagrangian mechanics so we can have a more complicated system, such as the double pendulum, which we will start on next class, and then try to control it. All right. So This is pretty good. This is pretty good, but we want to be able to take these equations and simulate it somehow, okay? And the EL RHS, the right-hand side, is equal to 0. Euler-Lagrange right side. Okay. Okay, got that. So if we want to, now we want to be able to simulate this system, okay? This means a few things. We need to be able to isolate the accelerations and solve for them, or specifically just solve for the accelerations, right? And the way that we did this in class, we talked about doing this, all right, is that we would try to turn the equation into something of this form. M of Q double dot is equal to everything else on the right-hand side, something that's F of Q dot, and any control input, any control torques or anything tau, I should say. And then you would solve by saying Q double dot is equal to M inverse of Q times F of Q dot, and tau. This is what we covered last time, right? That gives you your forward dynamics. So it's forward dynamics because you put in all of your forces and your current position and velocity, and out comes your acceleration. Right? So in order to do this, we have to put it in this form, where we have a bunch of Q double dots multiplied by a matrix. In this case, it's going to be a 1-by-1 matrix because there's only one generalized coordinate. And then we're going to get all the other terms together. So what we need to be able to do, my friends, is we have to be able to isolate this Q double dot, okay, and figure out what terms are multiplied by it, and the ways, what all the coefficients are in front of it. And the way that we do that is with the Jacobian. It's basically taking a partial derivative with each of the accelerations, okay? So what we're going to do, so we're going to go back to the code. Let's try taking our EL left-hand side. We ran our code, still works. Let's take our EL left-hand side. And we want to take the Jacobian of it, but with respect to our accelerations. So let's define our accelerations, all right? We have not defined our accelerations as a symbolic variable, but we totally can. Up here, we can say d dq is equal to the derivative of q with respect to time again. That's the syntax for a second derivative in the MATLAB symbolic toolbox, okay? So GDQ will now be defined. So if in the command window, if I said, hey, what is the Jacobian of our EL left-hand side with respect to DDQ, what does it give us? That ain't right. I don't think that that's right. Is that right? Actually, technically, I think it is right. Let me see if I can... It's right, but I want to make sure that like it's right for the right reasons here. Okay, let me try that for theta. Try it just for Q, see what happens. Yeah, well, okay, it works out fine. Good. Good. Works out okay, it seems. All right. So if we look at the EL left-hand side, here's our theta double dot. What's the coefficient in front of that? 1. So if I do the Jacobian of EL left-hand side, with respect to DDQ, 1. Okay? Guess what that is, my friends? That, my friends, is your mass matrix here. That's the mass matrix, the inertial matrix. So let's say our inertial matrix M is going to be equal to the Jacobian of the left-hand side, LHS, with respect to DDQ. Now, right now, this is assuming there's nothing on the right-hand side. So there's probably not going to be any acceleration terms on the right-hand side. There shouldn't be. But technically, you might want to subtract the right-hand side to put everything on the left-hand side to do this. But that's okay. And then this term over here, this F, is everything else, right? Which would mean that if we take our Euler-Lagrange equations, okay? Take our Euler-Lagrange equations, and wherever we see a theta double dot, we insert a 0. Okay? Then everything else, so that should eliminate all of the theta double dot terms and everything multiplied by them, right? Leaving only everything else. And then we got to put it on the other side, from the left-hand side to the right-hand side, so we're going to do a little negative on it, right? So what we're going to say is that F is going to be the substitution into the Euler-Lagrange left-hand side, where there was once DDQ. We're going to put in zeros of the size of DDQ. So if DDQ is a larger DDQ, the more accelerations, then the code still works. So we don't have to get the size right here. And sure enough, look, F of t, look at that. How about that? Isn't that neat? So there we go. We got to put it on the other side. So we're going to do a -1 times. So this is put on the other side. Meaning we took it from everything that was on the left side that's remaining, put it on the right side, which means we have to multiply it by -1, of course. Okay? Put it on the other side. Now we have M and F. Interesting. Interesting. So that means that we now have an M matrix and an F matrix. So if you want to solve for DDQ, for any particular theta and d theta, we have the M matrix, we have the F matrix. We could solve it with this trick. Okay? Now, we won't have time to simulate it today, actually show the simulation. There'll be a couple more steps. We'll do that, and we'll expand it to the double pendulum, and boy, does that get fun. The double pendulum is nifty. It's really cool, the way it flops around. Okay? Don't be lulled into a false sense of boredom by the single pendulum to count out the double pendulum. Nay. Nay. Double pendulums are awesome. They will flip-flop around. They're chaotic. All kinds of crazy things. I remember back in the days, there was a day back in the day, the heydays of Twitter, there was an account, it was a bot account that all it did was post simulation videos of double pendulums in different initial conditions and show all the different ways that they would flop around every day. It was a double pendulum bot account. And of course I subscribed because it was cool. In any case, that takes us to the end of the lecture. Good luck. Hope you notice the homework is up. Good luck with the homework. Please get moving on the trajectory optimization side. It can be tricky. Best of luck. Take care and all the best.